In this video, I'm going to talk about 10.1. I'd like you to read 10.1. It's a review. It's curves defined by parametric equations. So imagine a particle that moves along the curve C, shown in figure 1. It is impossible to describe C by an equation of the form y equals f of x because C fails the vertical line test. Right, you're hitting the line in this example 3 times. Okay, so it's failing this vertical line test. But we can define this as f of t, g of t. So we'll talk about that here. But the x and y coordinates of the particle are functions of time, and so we can write x equals f of t and y equals g of t. Since such a pair of equations is often a convenient way of describing a curve and gives rise to the following definition. Suppose that x and y are both given as functions of a third variable t, called the parameter, by the equations x equals f of t and y equals g of t. So you'll see that x is actually defined by an equation that has a parameter of t, and so does y. Okay? And these are called parametric equations. Each value of t determines the point x, y, which we can plot in a coordinate plane. As t varies, the point x, y, which equals f of t, g of t, varies and traces out a curve, C, which we call a parametric curve. The parametric t does not necessarily represent time, and in fact we can use a letter other than t for the parameter, but mainly t is used as a parameter. A lot of the times parametric equations are used for movement, positioning, and direction, and that really is contingent on time. So time is a main one, and then we'll talk a little bit about angle, t being angle. But in many applications of parametric curves, t does denote time, and therefore we can interpret f of t, g of t as the position of a particle at time t. Alright, so the example 1, we sketch and identify the curve defined by the parametric equations. We have x equals t squared minus 2t, and y equals t plus 1. Alright, so the first thing you want to do is you create this table, just like you create a table if you graphed anything. For example, t equals negative 2. You're plugging in negative 2 for t, for x, and you get negative 2 squared minus 2 times negative t, which will be 8. And then you plug in negative 2 for t in this equation for y, and you get negative 1. So your parameter value here is negative 2, and that gives you the point 8 and negative 1. Your parameter value of negative 1 will give you the point 3, 0. So this is going to end up tracing out a parametric curve. And just a side note here, we're talking about parametric curves, not just general curves, which is just a set point, but really a parametric curve in which the points are traced, in a particular way, right? So we're going from the time 0, which equals 0, 1, and then moving forward, and we're getting particular points for that time. So as if t equals 0, then x equals 0, y equals 1, and so the corresponding point is 0, 1. So in figure 2, we plot the points x, y determined by several values of the parameter, and we join them to produce a curve. Alright, so you'll see that you've got these arrows that have direction. That's what you want to do with a parametric curve, not just any curve. And you see how time increases, and as time increases, this curve changes direction as well. You got an inflection point here at 1, so it changes and goes towards the positive x and positive y, continues positive y. So a particle whose position is given by the parametric equations moves along the curve in the direction of the arrows as t increases, like I just mentioned. And notice that the consecutive points marked on the curve appear at equal time intervals, but not at equal distances. This is because the particle slows down and then speeds up as t increases, right? So it's slowing down and then increasing again. It appears from figure 2 that the curve traced out by the particle may be a parabola, right? So this can be confirmed by eliminating the parameter t as follows. So we can eliminate the parameter t and have an equation with respect to y, or multiple equations with respect to y. So we obtain t equals, alright, so we solve for t from the second equation and substitute into the first equation. Alright, so we'll get x equals t squared minus 2t. Plugging y in there for t, y minus 1 for t. Okay, so we get x equals, right, so we get the parabola, right, that x equals y squared minus 4y plus 3. Alright, so no restriction was placed on the parameter t in example 1, so we assume that t could be any real number, but sometimes we restrict t to lie in a finite interval. For instance, the parametric curve goes from 0 to 4, inclusive. So it's just part of the parabola here, right? So we're starting at 0, 1, right? Because at 0, your point is 0, 1, and then you're following the curve towards 8, 5, right? So for 4, you get the point 8, 5. Again, the arrowhead indicates the direction in which the curve is traced as t increases from 0 to 4. In general, the curve with parametric equations, x equals f of t and y equals g of t, goes from a to b. So your initial point is that f of a, g of a, and your terminal point is going to be the f of b, g of b. So what curve is represented by the following parametric equations? So you've got your x value being cosine of t, and your y value being sine of t, and you're going from 0 to 2 pi. Right? So if we plot the points, it appears that the curve is a circle. We can confirm this impression by eliminating t. Okay, so if we eliminate t, we know that x squared plus y squared, which is cosine squared plus sine squared, equals 1. Pythagorean theorem. Thus, the point x, y moves on the unit circle. X squared plus y squared equals 1. Alright, so we'll have a picture of this parametric curve. Notice that in this example, the parameter t can be interpreted as an angle in radians, shown in figure 4. So t no longer is considered time in this particular example with a circle, it's considered the angle. Right? As t increases from 0 to 2 pi, the point xy, which is cosine t, sine t, moves once around the circle in a counterclockwise direction, starting from the point 1, 0. Okay, so real quick here, so a circle with center with a center HK, alright, and radius R. Alright, the parametric equations for that is x equals h plus r cosine t, and your y is going to be k plus r cosine t. So and then your t, to get that circle, right? To get that circle, t is going to have to go from 0 to 2 pi. Unless you put some sort of constant in front of t here. Then you maybe, if you have a 2 in front of these, then you could go from 0 to pi. But so this is going to be, if you see something like this, you can right away spot that it's a circle with center HK and radius R. Right. Now, graphing devices, you can use your TI calculator or Desmos. So we're gonna just talk about graphing. Right? We can graph something like this in Figure 9. So I just went to Desmos, so I'm going to show you that. This here, you can see that we've got a graph, and we can go from -2 to 2, and it looks like this. Now if we just go from, say, -1 to 2, you see how the graph gets cut off here. So we can go to 1, and it gets cut off even more. We could go up to -4, 4, changing the parameters, and it'll spread out even further, right? So it'll continue to go on, depending on what your parameter for t is. Great. So Desmos is a good online graphing tool for something like this.